Hi everybody. Earlier we looked at how to calculate the Fibonacci sequence using a recursive approach, and we also looked at how inefficient the recursive approach actually is. We saw that for even moderately sized numbers like 20, 30, or 40, the amount of calculations needed just becomes way too high for most computers to really handle. So in this video, we're going to continue our look at calculating the Fibonacci sequence, but we're going to look at a few more efficient variations that make up for the shortcomings of the recursive approach. Now, one of the big reasons our current recursive approach is expensive is that it does a lot of duplicate work. In many of the paths our recursive call takes, we are calculating and recalculating the result for an operation even though we have already calculated it earlier. So let's take a look at the function call tree for Fibonacci 5 that we saw earlier. Notice that I've highlighted the number of times Fibonacci 3 and Fibonacci 2 are being called over and over again. Now, in an ideal world, except for Fibonacci 1 and Fibonacci 0, for which the calculation has already been provided for us, imagine we could remember the value of what happens when you calculate a third Fibonacci number or the second Fibonacci number, and the next time you encountered it, you just reused it wholesale as opposed to calculating it from scratch again. If we had done that, except for maybe the first two boxes for Fibonacci 3 and Fibonacci 2, the entire subtree to the other right side, for example, would completely disappear because we would have cached the values that are involved. And so this caching technique that we can use to kind of calculate a value and remember it has a name. It's known as memoization. It's like memorization, but it's not. It's memoization. And it's a programming technique that involves storing the results of expensive function calls so that they can be reused later. And to put it differently, it's a way of optimizing a function by reducing the number of times it needs to be called. And so let's walk through the code very briefly. And for all the code snippets I'm showing, you'll see more of it on crypto.com or in my book where I explain it in much greater detail. It's kind of hard to go through code in a video, but I'll just walk through the high level pieces of it so you can kind of match the explanations with the syntax that you ultimately see. So here we have a version of Fibonacci, in which case we are finding the number, but we're also caching calculations we've already done to speed up and avoid duplicated lookups. So notice that we have at the very top an array called cache, and it stores the result of each calculation we make. Each time we're about to make a recursive call, we first check to see if we already have a result stored in our cache array. That's the first if statement you see there. And if we don't have the result stored, then we do the full recursive call, and where we go through what looks almost like the code you saw earlier for the recursive version of Fibonacci, where we're making sure that if the value is either 0 or 1, we find the value is less of it, and then we do the caching. We see if it is going to be the n-1 or n-2 value, run it fully through completion, and then store the calculated value. And so by relying on memoization, where we store the results of calculations we have already made, we greatly reduce the number of unnecessary work our code does. And so we saw earlier that calculating the 20th Fibonacci sequence resulted in 13,529 calls, in the purely recursive approach. By combining the recursive approach with memoization, we made a total of just 37 calls. It's not a made up number. It's not a, misspeaking here. It's 37 calls. That's a whopping 99.7% reduction in the amount of work that we're doing. And so if we go back to the example, I talked about earlier, the way you look at it is that by using memoization, we basically ignore large amounts of work, which I don't know why, but I used the picture of a koala to kind of block out the entire tree that we don't need to worry about, where you can see that from this many calculations and recursive calls to only a handful, and this is only for calculating the fifth Fibonacci number. So you can imagine for much larger values how much more the optimization will make. 99.7%, as we saw earlier with the previous calculation that we talked about, which is nothing to sneeze at. That's quite a big optimization. Now, that's one way of optimizing, which is recursion with memoization. There is another approach, and the final and fastest approach we will look at is one where we kind of go avoid recursion completely, and we take an iteration-based approach. In an iteration-based approach, we use a loop, such as a for loop or a while loop, and completely avoid calling the same function we're in over again. So there's no call stack, or there's no overflowing of the call stack and multiple function calls and things like that. And the code for this looks as follows. And the iterative approaches typically look more complex because recursion is easy for us to wrap our heads around. With iteration, there's a lot of calculation and wrangling we're doing, on our own within the same function. But the general idea of what this code is doing is exactly the same as what it was when we talked about how to calculate Fibonacci sequence earlier. The only variation is where you can see that we have the for loop at the middle. That for loop is what replaces the recursive calls earlier, where the end result is still we're adding the values of n-1 and n-2 in a very nice way, and the result, of course, is going to be the same answer. It's just going to be much faster. How much faster is this approach? Well, let's go back to our chart earlier. So from what we've seen so far, the fastest approach for calculating the Fibonacci sequence is kind of hard to see here, right? We can see that we're seeing the number of recursive calls here, and you can see that the time in milliseconds, which is kind of corresponding to the number of function calls, it's pretty much like astronomical for the recursive approach. And then for the recursive and memoization approaches and the iteration-based approaches, you really can't see much here, right? The chart pretty much looks like a straight line. And that's because it's really unfair. When you have an alpha in the room like recursive, any comparison, let's say go on like a logarithmic scale, will not even register as a blip on this chart. So let's go ahead and ignore recursive for now. We know recursive is terrible. Let's not harp on it. So let's take recursive out and focus our attention on just memoization and iteration approaches. And here's the number for calculating the Fibonacci sequence for the first 300 numbers. And notice the time that we see here. You can see that as our numbers keep increasing, the iteration-based approach is just a much faster solution. It doesn't seem to be growing linearly at all, or even, sublinearly. It's actually almost flat, I could say. And the reason is that for the recursive memoization call, it's faster than the pure recursive approach. But even though it's recursive memoization, there's still more function calls, still more work to be done. So you can see it's still faster than pure recursive, but much slower than what we saw with the iteration approaches. And the reason is that no matter how effective our memoization strategy is, recursive function calls are just expensive operations. And if we're going to avoid them entirely, like we're doing the iteration-based approach, we will get the best results. And so the problem with recursion is that it can be slow. This is especially true when we're dealing with large inputs or complex calculations that result in many recursive function calls. And to address this, we saw two other approaches, which is recursion memoization or going full on iterative. And so when we looked at all of these optimizations in the context of calculating a number in the Fibonacci sequence, the concepts that we saw here will continue to carry over into other problems we'll be seeing in the future, especially other algorithms that do a lot of number crunching and many calls that are very similar to this. So it's going to be a fun ride. And so, of course, if you have any questions on anything you've seen here or want me to go deeper on any topic, the best place to post about it is on the forums at forum.curve.com, where I and others would be very happy to help you out and answer any questions you might have. And before I wrap this up, as always, you probably know the drill by now if you're watching my other videos. Here's some links you can take to be up to speed on all the content I create on a regular basis, whether it is liking, commenting, and subscribing on this video, signing up for my newsletter, or finding me on all the various social networks. I'm typically at Krupa on all of them. And if you enjoy reading in-depth topics on web development, animation, or just data structures and algorithms like you might have seen earlier, by all means, check out the books. All links for all these things are going to be posted below. And with that, I will see you all next time.